Hi everyone, let's continue to talk about surface integral of scalar value functions. Let S be a surface with parameterization R of u v equals, so we have three coordinates, x, y, and z. They are all functions of u and v. Okay, so this surface, let's say R of u v, we have it over some parameter domain D. Okay, so we have the UV plane, and that is our domain D. We assume here and throughout that the surface parameterization R of UV is continuously differentiable, meaning each component function has continuous partial derivatives. Assume for simplicity that D is a rectangle, although the following material can be extended to handle non-rectangular parameter domains. Okay, next we can divide the rectangle D into subrectangles Dij. Okay, with the horizontal width change of U and the vertical length change of V. Okay, so we can divide it. And now we can form a grid with lines that are parallel to the U-axis. So these are the grids parallel to the U-axis, and the grids that is parallel to the V-axis in the UV plane. Okay, these grid lines correspond to a set of grid curves on the surface S. See, for example, this guy corresponds to this grid curve, and this guy corresponds to this grid curve on the surface, right? Without loss of generality, we assume that Pij is located at the corner of two grid curves. So this is the point Pij. Okay. If we think of R as a mapping from the UV plane to the space, the grid curve are the images of the grid lines under R. To be precise, consider the grid lines that go through the points UI, Vj. One line is given by x equals UI, y equals v, and the other one is given by x equals to u, y equals Vj. For example, here, okay, so we look at, so this vertical line, we will have x equals u, right? And I, okay? So if we suppose these points, so this point is UI, Vj, this vertical line is x equals UI, and then this horizontal line is y equals Vj. Okay? And let's continue. Okay, so here, any point on a point on this vertical line, we know the x coordinate is fixed as UI, but the y coordinate can be varied, so it can be v. Okay, and let's say on this point, the point on this line, the y coordinate is fixed, that's Vj, but the x coordinate can be varied, that's the u. Okay, so let's look at the next picture here. Okay, so in the orange line, okay, so in the orange line, the horizontal component u is held constant, and the vertical component v varies. Okay, so this is the orange line. Okay, so this orange line, we have x equals u0 and v varies, right? So that's why it yields a vertical line through the points ui, vi. In the blue line, so the blue grid line, the vertical component v, so v is constant. The horizontal component u is it varies. Okay, u varies. There's no x here. Yielding a horizontal line through ui vj. The corresponding grid curve are r of. Okay, so here, let's see. This any points here, we can use ui v, right? So that's why the corresponding grid curve is r of, so here r of ui v, right? And on the other points, let's say because vj second component is fixed, first component varies, so then corresponding here we have r of u vj. And so this is one variable, this is also one variable, so that's why they are curves. Okay, so they are curves and they intersect at the point pij. So far so good. So this is pij, and this point is ui vj. Okay, then don't look at this. So far so good, everybody. Okay, now consider the vectors that are tangent to this grid curves in the space. For the grid curves r, ui, v, so v varies. The tangent vector at pij is, well, so look at this orange grid curve. What do you see the tangent vector? Well, the tangent vector, because v varies, u is fixed, so we get the tangent vector in the v direction. So that is the derivative of our parameterization with respect to v. Okay, we let u be, we consider u is like a constant. So u is like a constant and v varies. Okay, so v is a variable. So v is a variable. Okay, so we get tv. And then for the other grid curve, r, u, vj, which is this guy, this blue one. Okay, you can see the v is fixed, so v is like a constant, and u is the variable. So that's why the tangent vector is in the u direction. So tu is the parameterization. We take the derivative with respect to u. So that's xu, yu, and zu. So far so good, everybody? Okay. So those two tangent vectors are in the space tangent to the grid curves. Okay. Now, consider the vector tu cross product with tv. Well, this is the normal vector, right? And it is not 0. And then, so the tangent plane at pij exists. You see, this is the end. The tangent plane is somewhere like here. Okay? If the piece Sij is small enough, then the tangent plane, see, if we zoom in, and this is our picture. Okay? So we have the tangent plane here, and then the surface patches here. They're quite close to each other. They're very, so the tangent plane at that point will be a good approximation for the pieces Sij. Now, if we consider an increment change of u with v fixed, the tangent vector tu change of u forms one side of a parallelogram. Similarly, with an increment change of v with u fixed, we get tv change of v forms the other side of the parallelogram. So this guy, this is the surface area, the change of the surface area. It's approximated by, the cross product is the area of the parallelogram, right? Cross product is area of the parallelogram. And that equals, because change of u and change of v, they're just scalar, they're just number. We can put it outside of the magnitude. Okay, so that's why this is what we get. Therefore, when we sum all those small area, we get the surface integral. Okay, so surface integral is the limit when this change of s goes to 0, and then we have the sum f of x, y, z, and each of x, y, z are a function of u and v. And then we have this surface area differential. It's not only the area differential. When we're talking about area differential, so dA area differential, we mean it is in the xy plane, right? And it's flat, okay? Or it could be r dr d theta. But here is the surface area differential. Surface area differential is the magnitude of the cross products of tu and tv, and then we have the du and dv. Okay, so hence we have let u be a continuous function on a smooth surface S given parametrically by r of uv equals x, y, z, where d, the domain, is like a rectangle. Assume also the tangent vector tu is the derivative of r with respect to u. Tv is the derivative of r with respect to v. Okay, but then they're both vectors. And assume they're continuous on the region D. Then, and the normal vector n is non-zero on D. Then the surface integral of f will equals, we have the double integral over the region S, f of x, y, z ds. Well, that is the same as f of x, y, z, and this is this dA. dA is the area differential, okay? ds is the surface area differential. And here, dA is just area differential. Okay, so area differential. dA in this case could be du, dv, or dv, du. And maybe it's also useful to have a picture in mind. On the UV plane, we have the rectangle, right? This rectangle and this region, we call it D. And then the parameterization, we can map it to a surface patch S. So S is in the space. So far, so good, everybody? Okay. So now let's look at our example and let's see how we use this big formula to compute the surface integral. Find the surface area of the cylinder between the plane z equals 0 and z equals 16 minus 2x. Okay. So surface area means the inner function is 1, right? Okay, now let's see. Let's draw the picture. So x, y, z. This is a cylinder with radius is 4. So radius is 4. And then we go up like that. Okay. Between the plane z equals 0, or z equals 0 is the xy plane, right? And 16 minus 2x. Well, 16 minus 2x is on the xz plane. Xz plane, right? If x is 0, we get z is 16. And then when z is 0, we get 16. So when z is 0, we get 16 minus 2x equals 0, x equals to 8. So 8 is right here. Okay, let me draw a better picture. So let's say 16 is here. Okay. Okay, because this have to be longer. Let's say 16 is here, A is there, and then this is the line z equals 16 minus 2x on the xz plane, and then you imagine how this. We imagine this is a plane, right? And how this plane will cross the cylinder. Let's draw it. Sometimes it really needs our imagination. Think about this 4, right? If 4, it will match this point. Okay. So this point corresponds to x is 4. Then z will be 16 minus 2 times 4 is 8. Okay, so this corresponds to that. And so, and here, well, on the other side, we get when x equals to minus 6, then minus 4, then z will be 16 plus 8, which is it 24? Okay, so then it's something like this. Can you imagine? It's like the cylinder, and then we cut it. We cut these pieces, and we cut the bottom pieces. Okay. All right. So how do we find a parameterization for this surface? Well, it is on the cylinder, right? So we can let one of the variable be theta. So let's let u be theta. So far so good, everybody. And let v be z in this case, okay? Because r is fixed. Then x will be r cosine theta. R is fixed, so 4 cosine u. Y is r sine theta, so 4 sine u, and z will be v. Okay, our parameterization uv equals, oh, by the way, sometimes I forget the arrow. Oh, but in this is actually a vector value function, okay? So keep that in mind. 4 cosine u, 4 sine u, and z is v. Okay? U is between 0 and 2 pi. Okay? But the v is actually depends on the u, because v, see, look at the z is from 0 to 16 minus 2x, right? So z is from 0 to 16 minus 2x. Then v is then from 0, 16 minus 2x. But what is x? Well, x is 4 cosine u. So this is the same as 16 minus 8 cosine u. So far so good, everybody? Yeah, so v really depends on u. So when you set up the surface integral, you need to have du outside and then dv inside. Then u is between 0 to 2 pi, and then v is between 0 to 16 minus 8 cosine u. Okay? So far so good? Alright, so now let's figure out what's the question mark. Surface area, so our function is 1, but we still need to figure out, so the function, and we also need to figure out tu and tv and the cross products and the magnitude of the cross products. Okay, so let me use a different color, then you can see between my different steps. So here, after we get the parameterization in u and v, so let's figure out what's tu. Tu is a vector. And we take the derivative of each component with respect to u. Derivative of cosine u is minus sine u. Derivative of sine u is cosine u. Derivative of v with respect to u is 0. How about tv? Derivative of cosine u. Oh, there's no v in it, so 0, 0. Oh, that is 1. Okay, so what is the cross product? Ooh, do I almost run out of space? Yes, I do. Let me create more room. Yes, it will help me to create more room in this case. So far, so good, everybody. All right. So tu plus tv, that's I, j, k, minus 4 sine u, 4 cosine u, 0. 0, 0, 1. Okay. So what do we get now? You can see that is the j component times what's the submatrix? Ooh, we can actually calculate it, right? So that's 4 cosine u times 1 minus 0. And then minus j, well, then times the determinant of submatrix. Oh, you see? It's minus 4 sine u times 1, so it's negative. Because the negative become positive. And k, oh, you see? K, this guy, the determinant is 0. So we just get 4 cosine u, 4 sine u, and 0. So far, so good. Then what is the magnitude of it? Well, it's the square root of every component square. 4 square sine u square. Well, you know, sine square plus cosine square is 1. So this is the same as square root of 4 square. So that is just 4, right? Okay, we're ready because the surface area. Okay, so surface area equals, see, our function 1 is 1, right? Because we're looking at the surface area. Okay, so the function f is 1. Let me put it down here. This is f is 1. And the magnitude of tu plus tv is 4. Right? And then here, because v is a function of u, we have to do dv and then du. And then v is from 0 to 60 minus 8 cosine u. V is from 0 to 60 minus 8 cosine u, and u is from 0 to 2 pi. Yeah? That we just get from here. Okay, now let's start to calculate this double integral. We move the 4 outside. So integral of 1 with respect to v is just like v. Evaluate from 0 to 60 minus 8 cosine u du. Okay, and so we have the upper 16 minus 8 cosine u. When you plug in v is 0 du. So that is 16u minus integral of cosine is sine. So sine u. Evaluate from 0 to 2 pi. So we plug in 2 pi, when we plug in 0 is gone. And sine of 2 pi is 0, sine of 0 is 0. So this is our answer. What is that? 128 pi. So far, so good, everybody. So actually, in this example, we understand that that our theorem holds. The D is not necessarily a rectangle, and you can see in this case, D is not a rectangle. Our V is actually a function of U. So far, so good, everybody. Yes. So let's summarize the steps again. First, we want to draw the picture and construct a parameterization. Of course, you want to, if there are several parameterizations, you want to pick the easiest one. right? If there is a way that you can avoid, like the easiest case is when two of the variable are between two numbers, constants, okay? But sometimes we're not able to do that, then it's okay. Just make sure your order, okay? So here v is a function of u. Then when you set up the surface integral, the du is outside, the dv is inside. Okay, the second step, after we figure out the parameterization, we find the derivatives with respect to u and with respect to v, and then we compute the cross products and the magnitude of the cross products. The last step, we can compute the surface integral. Okay, because we're looking at surface area, so the f is 1. But if f is not 1, then you say surface integral instead of surface area. So far, so good, everybody. Okay, let's do more examples. Okay, so let's look at this picture. So evaluate the surface integral where s is the cylinder, x squared plus y squared equals 4. And z is between 0 and 3. So it's better to use, so this is a cylinder, right? So it's better to use like a cylindrical coordinates. And we should let u, okay? So let me draw a picture here. So this is the cylinder with radius 2, z is 3. Okay, so let u be like a theta, and then z is z, v is z, then x equals r is fixed, r is, so you can see r is 2 in this case. So it's 2 cosine theta, y is O, and theta is u. 2 cosine u, y is 2 sine u, z is v. So our parameterization equals 2 cosine u, 2 sine u, v. And u is our theta. It goes from 0 to 2 pi. V is our z. It goes from 0 to 3. Oh, we have rectangle region. That's nice. Okay, so now what is tu? Well, tu, the derivative with respect to u, we have derivative of cosine is minus sine. Derivative of sine is cosine. Derivative of v with respect to u is 0. And then tv is 0, 0, 1. So far, so good, everybody. Okay, what's tu plus tv? Well, I, j, k, minus 2 sine u, 2 cosine u, 0, 0, 0, 1. Okay, I'm gonna do it quick. Okay, see whether you can follow. I, determinant of this guy. Well, 2 cosine u, right? And then negative j, determinant of this guy. But this is negative 2 sine u, but negative become positive. So 2 sine u. And then last, the k component is the determinant of this submatrix. Because it has the entire row of 0, the determinant is just going to be 0. So this is the cross products. What is the magnitude of this cross products? So 2 square cosine u square, 2 square sine u square, sine square plus cosine square is 1, square root of 2 square equals 2, right? You see this process is quite similar to our previous examples, right? But now let's see our surface integral equals x. What is x? x is 2 cosine u. Y squared, so 4 sine u squared. This is our f, right? And then times, what is that? The magnitude of the cross products. And then, because we have a rectangular region, du, dv, du doesn't matter. Let's do dv du. V is from 0 to 3. U is from 0 to 2 pi. Okay, we can pull, let's see here. What can we do? We can pull this 2, and because this 2 term has the factor 2, we can actually pull out 4 outside. And then we get 0 to 2 pi. And here, what's left? Well, we just have cosine u plus 2 sine square u, and because this is like, this guy has no v in it, so it's like integral of that is just v from 0 to 3 du. Well, v from 0 to 3, we plug in 3 minus 0. It just gives us a factor of 3 in front. So 12. And then cosine u. You know, what is 2 sine square u? That is actually, I ran out of space. Can I move a little bit space? Oops. So that is actually 1 minus cosine 2u du. Why is that? We're using the formula that cosine squared is 1/2 plus 1/2 cosine 2 theta. Sine squared is 1/2 minus 1/2 cosine 2 theta. So 2 sine squared is 1 minus 1 cosine 2 u, okay? Alright, we're ready to integrate. So, integral of cosine u is sine u. Integral of 1 is u. Integral of cosine is sine 2u, but divided by 2. Evaluate from 0 to 2 pi. Sine 2 pi is 0, sine 0 is 0. And u plug in 2 pi. U plug in 0, 0. Sine 4 pi is 0, sine 0 is 0. So the answer is 24 pi. So far, so good, everybody? Okay, yeah, I hope before we go over each example, you can try the problem first, and then you can continue to watch the videos and check your answers. So let's continue. Please work on this problem first, and after you're done, you can continue to play the videos. Have you done? Okay, let's check our work. Okay. So we want to calculate this surface integral, where f equals z squared and s is the surface that consists of the piece of the sphere that lies on and above the plane z equals 1. Okay, let's draw the picture. That is the sphere with radius 2. I mean, radius is like rho, right? Rho, radius of a sphere. Okay. Alright, and z is 1. So this is 2, this is 2, this is 2. Z is 1 is right here. Okay? So lies on and above. So above is only these pieces. So far, so good. And for sphere, do you remember how do we parameterize it? We let u be phi, let v be theta, right? And then our parameterization is Rho is 2, right? So 2 sine phi cosine theta. Oh, sorry. We should plug in u and v, right? So cosine v, and then y is 2 sine u sine v. Z is 2 cosine u. So far, so good, everybody? Okay, now let's see. What is the u? Well, u is the angle phi, right? So u is the angle phi. Phi, see, think about the angle. Well, it is from 0 to, what is the biggest can it reach? Well, this guy is like here. This is pi over 4, right? So u is between 0 and pi over 4. And v is theta. Theta is from 0 to 2 pi. Then we only look at the surface of these pieces. So far, so good, everybody? All right, let's continue. Oh, wait a little bit. I think I just make a mistake. Let's in fact draw it. So let's draw it. Here, we have, this is 2, right? And this is 1. And we have this guy. Oh, this is 2 as well. So here is 1. So far, so good, everybody? This is phi. What is this angle? So this guy, the length is 2. Well then, this guy is 1. Look at this. This is like the adjacent to hypotenuse. So cosine phi is adjacent is 1, hypotenuse is 2. Then what is this angle? Okay, that is actually pi over 3. It's not pi over 4. So we have to be very, very careful. Yes. Sometimes we need to draw the details, then we can figure that out. Okay? Yes, check it carefully. All right, let's continue. Oh, I understand why. So here, because we are intercept with the plane z equals 1, if we're intersecting with the cone, so let me use a different color here. Okay. Oops, sorry, I dropped my pen. Oops. Okay. So let me put it down. If we want to intersect with the cone, z equals square root of x squared plus y squared, then we will have the picture like this. This is the cone, and then we will get pi over 4. Okay, but now it's not the cone. It's only the z equals to 1. So this is pi over 4. Sorry, pi over 3 instead of pi over 4. Okay, so let's continue. Let me get back with my orange color. Okay, let's continue. So we get the parameterization. Next, let's find TU. Well, the derivative is back to u. Derivative of sine u is cosine u. Derivative of sine u is cosine u. Derivative of cosine u is minus sine u. Yeah, we're gonna do it slowly because this parameterization derivative is not that easy, right? It has a lot of terms. We have to slowly. Derivative of cosine v is minus sine v. So sine u sine v. Derivative of sine v is cosine v. Derivative of cosine u, it has no v in it, so it's 0. So what is the cross product? So cross product, we do I, j, k, 2 cosine u cosine v, 2 cosine u sine v, minus 2 sine u, minus 2 sine u sine v, 2 sine u cosine v, 0. Now what happened? Let's see. So I, then the determinant of this submatrix. So 0 times that is 0, minus, negative become plus. So we get 4 sine u squared cosine v. Is that okay, everybody? And then minus j of this guy. 0 times that is 0, minus 2 negative become positive, but it's negative j and minus that, so negative also become positive. We have 4 sine u squared sine v. Okay, so there are 4 negative here. So this is one negative, this is another negative, and there's a negative of the j component, and you know that the determinant is this guy minus that guy, so there are 4 negative there. It makes the answer to be positive. So far so good, everybody. Okay, let me erase these circles. Okay, then the k component. What is this guy? This guy times this guy. 4 sine u cosine v squared, minus negative become plus. 4 sine u cosine u sine v squared. Well, you see, they have a common factor. Cosine squared plus sine squared is 1. So this guy is just 4 sine u cosine u. Okay, now let's figure out the magnitude of it. All the terms square. Now let's see what it is. 4 squared, 16, and sine to the 4th, cosine v squared. 16 sine u squared, sine to the 4 sine v squared. Yeah, this is a lot of u and v and sine cosine everywhere. We have to calm down, take a deep breath, and sometimes if you want to go to the restroom, yes, take a little break and come back and continue. Yes. Okay, and last term, 4 squared is 16 sine u squared cosine u squared. I don't need that long. Okay, so do you see this guy and this guy is the same? We can factor it, and we know cosine squared plus sine squared is 1. So this is just 16 sine u to the 4. And do you see now they have common factor 16 sine u squared, and then after you factor out, we just get sine u squared plus cosine u squared, and that is 1. So just get square root of 16, which is 4. Square root of sine u square cancel. We just get actually absolute value of sine u, but don't forget u is like our phi. So in general, phi is defined to be between 0 and pi. You know, sine from 0 to pi is positive. So this is just 4 times sine u, because sine u is greater or equal to 0. Is that okay, everybody? Yeah, you have to be careful when you take square roots of a square. It's actually absolute value, and then to get rid of the absolute value, you have to think about, oh, the things inside the absolute value, is it always positive? Or if sometimes negative, then you have to break it into cases. Okay, finally, our surface integral. What is the f? Z squared. Okay. So, surface integral. Shall I use a different color again? Yep, please, a lot. So, in different steps, I'm using different color. Okay, so surface integral. That is, so here we get a rectangle, u and v are between two numbers, so du, dv, or dv, du doesn't matter. And f is z squared. Z is, what is z? 2 cosine u. So 2 cosine u squared. 4 cosine u squared. That is the f. Times 4 sine u. 4 sine u is the magnitude of the cross products. And then we can do du, dv, or dv, du. V is between 0 to 2 pi. U is between 0 and pi over 3. Okay. Oh, we can see we can factor out 16. And what's left? So integral from 0 to pi over 3, and then we have cosine u squared, sine u. So because we have no v in it, so integral of constant with respect to v is just v. Evaluate from 0 to 2 pi du. It's like we plug in 2 pi, subtract 0, so it's like we multiply by 2 pi in front. We have 32 pi. Integral from 0 to pi over 2, cosine u squared, sine u du. Do you realize the derivative of cosine is negative sine? So here is like a u substitution, abuse of notation. Let's call w is cosine u, then dw is minus sine u du. Well, then this guy equals 32 pi. We have w of 0. W of pi over 3, w squared, sine u du is minus, so negative, put it in front, dw. Well, this is w cubed over 3. W of 0, cosine 0 is 1. W of pi over 3, cosine pi over 3 is 1/2, right? So that is minus 32 pi, plug in 1/2, so we get 1 over 8 divided by 3, so 1 over 8 times 3, minus, we plug in 1, we get 1. Oh, so distribute, we get minus 32 over 8 is 4 pi over 3, and then plus, oh, don't forget the 3 here, 32 pi over 3. So far, so good, everybody. And 32 minus 4 is 28 pi over 3. So this is our surface integral. So far, so good, everybody. Yeah, I would say the spherical coordinate one is the hardest parameterization, because you do have a lot of sine, cosine everywhere, and sometimes you have to be patient and slow down. If you write a u instead of, well, if you have a mistake writing the u instead of v, then you won't get a nice like simplification, because Yeah, we know sine squared plus cosine squared is 1, but this is only true when the angle are the same, right? So yeah, so when you write the u and v, be careful, don't mess up. Okay, so calm down, do it slowly, and check your work. Yeah. Okay, so let's review. First, we need to find the parameterization for it. Okay, we also need to figure out the UV, the bounds for the UV. Okay, is U a function of V or is V a function of U? In that case, you have a fixed order, right? And then we want to find the tangent vector in the U and V direction. So we take the derivative of our parameterization with respect to U and with respect to V. And then we compute the cross products and do some simplification. After that, we compute the magnitude of the cross product. And then when we set up the integral, the double integral of f times the magnitude of the cross product, and then it's dv du or du dv, depends on do we have a fixed order. If not, then which order doesn't matter. And then we can evaluate the integral, and remember, like some techniques like U substitution, that's the common one. Alright, so some other techniques like integration by parts, trig substitution, partial fractions, we don't see them quite often. Yes. Okay, so that's the surface integral for functions. Okay, so we will talk about the surface integrals for vector fields in the next video. See you soon. Bye.